These springs are suitable for applications requiring low spring rates and low pressure. Lee Spring carries a wide range of stock springs and has engineers available to support custom designs. No matter what your spring needs are, you can count on Lee Spring to provide you with the highest level of customer service and engineering support. If you would like to learn more, view our other spring knowledge sessions, refer to our catalog, visit us online at www.leespring.com, or call us at 888-SPRINGS. Various aspects related to spring principles and design. In this series, we will cover the most popular type of spring, the compression spring. In Module 1 of our series, you will learn about what a spring is, principles of spring design, spring rates, the primary elements of spring design, the process known as spring setting, and compression type springs. Now, let's get started. To understand springs, it helps to understand what a spring is. A spring is essentially a mechanical object that deforms when acted upon by an external force, and then returns to its original shape when the external force is removed. Each spring design has a unique function, and in the case of the compression spring, the primary function is to push. Now some basic principles of spring design. There is a principle of spring design known as Hooke's law, which relates to load and deflection. Essentially, Hooke's law states that a restoring force due to a spring is proportional to the distance the spring is deflected and acts in the opposite direction. Another important principle related to spring design is spring rate. The spring rate is the ratio of force per unit of deflection. Let's take a further look at spring rates now. Spring rate is a change of load or force per unit deflection as the spring is compressed. As an example, spring rate may be specified as the amount of force to move a spring 1 inch. A standard helical compression spring has a spring rate that is essentially linear over most of the operating range. The first and last few percent of the spring's deflection has a non-linear rate. When a spring reaches solid height, the spring coils are at a stop against each other. When talking about spring rates, this is generally the spring rate between 20% and 80% of available deflection. Now let's take a look at some of the design elements related to compression springs. One primary design element is the direction of wind. A coil spring can be wound in either a left-hand or right-hand direction, similar to a screw-type thread. A left-hand wound spring will spiral in the same direction as a left-hand threaded screw. A right-hand wound spring will spiral in the same direction as a right-hand threaded screw. Direction of spring wind can be important depending on how the spring is used. To determine the best wind direction, consider the application. For example, coil wind is important when you have one spring working inside of another. To keep the springs from binding against one another, the wind of the inner spring and the outer spring should be in opposite directions. If a spring screws into a threaded component, match the direction of wind to the direction of threads. Now that we have looked at how the spring is wound, let's take a look at other design elements. Spring squareness. Spring squareness is defined as the angular difference between the outermost limit of a spring diameter when compared to a straight edge at the right angle to a horizontal flat plate on which the spring is standing. Spring parallelism relates to the ends of the spring and how parallel they are to one another. Now let's take a look at the physical dimensions of the spring, specifically spring diameter. Spring diameter is often referenced in a couple of different ways. One method is the outside diameter, or OD. This dimension is important when the spring is used within a cavity. Another dimension is the inside diameter, or ID. This dimension is important for springs that work over a rod or shaft. The next type of diameter is the mean diameter, which is most often used for calculations for stress and deflection.